Today we're going to start looking at gas laws. In the last chapter we looked at solids, liquids, and gases. This chapter is going to focus all on just the gases. And the reason is gases are affected more by pressures and temperatures because there's so much empty space between them. So there's a lot more we can do with gases and a lot more we have to learn about them. First of all, you get a little background information. If you want to follow in the textbook, it's on page 361. Air is composed of lots of different kinds of colorless gas. But some gases do have color. Chlorine is like a yellow, green color. Nitrogen dioxide is a brownish red. And this is known as smog. And if you're watching the Olympics out in Beijing, you saw some smog. If you've ever seen a picture of Los Angeles, the actual smog is pollution that's trapped within the natural barriers of Los Angeles, or the mountains. So the pollution tries to rise above, but these mountains are keeping it in. And that pollution we can actually see, and it's called smog. And some days are worse than others, depending on how the wind blows, because sometimes wind can just blow it right over the mountains. Sometimes it just gets stuck there, and it's a very, very, very disgusting day when all you can see when you look over LA is brown air. Now we also know that any 1 mole of the gas is 22.4 liters. So that's information we already know. So what we're going to take a look at is this kinetic molecular theory of gases. On page 329, they explain what that is. And it's a theory about matter that states that particles of matter are always in motion. A theory about matter that states that particles of matter are always in motion. That's what kinetic is. Kinetic is the energy of motion, the energy of movement. The other one is called potential, and that's the energy that's they're ready to move. Okay, so this is kinetic molecules, so moving molecules. We're going to focus primarily on gases here. We're going to talk a lot about an ideal gas. It's a hypothetical, just like your ideal situation, hypothetically, but it perfectly fits all the assumptions of this model. And in real life, they don't always fit it exactly. But when we're talking about here, in order to understand what this model says, we're going to assume everything is an ideal gas, that hypothetically everything is just perfect. And here's some of the things that the kinetic molecular theory states. Okay, one is that gas consists of large numbers of tiny particles that are far apart relative to their size. Large numbers of tiny particles that are far apart relative to their size. Okay, number two, collisions between gases are always elastic. An elastic collision is one where there's no net loss of total kinetic energy. So, like a tennis ball, if you dropped it, it would bounce up, but it's not going to bounce as high as where you dropped it from. It's going to continuously bounce lower and lower and lower. So that's losing kinetic energy. Gas particles don't do that. When they hit each other, they come back right where they started. Okay, they're 100% elastic. So an elastic collision is one where there's no net. An elastic collision is one where there's no net. Loss of total kinetic energy. The next thing, the third thing it says in the kinetic molecular theory, so gases are in constant, continuous, rapid, random motion. Continuous, rapid, random motion. They are always moving in whatever way they feel like they want to go. The fourth part of the kinetic molecular theory says there are no forces of attraction between gas particles. There are no forces of attraction between gas particles. So they're not trying to stick together at all, like Cheerios in the bottom of a bowl of milk. They're not going to stick together at all. They're just wherever they are, they've got their own thing going on. 5, the temperature of a gas depends on the average kinetic energy. So the more energy you have, the hotter it's going to be. So it depends on the average kinetic energy of the particles of gas. Okay, and I said this is all for assuming ideal gas behavior. Real life, we get these real gases, and they don't always behave according to these 5 assumptions of the kinetic molecular theory. But for this chapter's sake, and for the sake of learning what these are, we're going to assume all gases are ideal. So the first thing we're going to talk about in this chapter is pressure. Pressure is the force per unit area on a surface. Force per unit area on a surface. So if you were to write it in equation form, it'd be force over area equals pressure. So what they're saying is, as the pressure goes up, you have less area. Area is going to go down. If the pressure goes down, the area goes up. They have a picture here of a ballerina. She's standing on both her feet. A lot of area for both of her feet, so the pressure's not too bad. Whereas if she goes up onto her toes, there's less area touching the ground, so it's going to hurt more. Okay, there's going to be more pressure on those toes. And on the last picture where she's just on one set of toes, there's not a lot of area at all, so it's going to hurt even more if there's a lot more pressure. If you've ever sat on a bed of nails, they have them at museums such as Franklin Institute. And you can lay on a bed of nails. Is what they do is they put plexiglass over it. You lay in the plexiglass, you hit a button, and the plexiglass goes away. But laying on a bed of nails, it makes you feel a little prickly, but you don't actually feel pain from the nails because your weight is distributed throughout all the nails. Whereas if you stepped on a nail, you would definitely feel pain because all of your weight is on that one tip of that nail, very, very small area. So the more area you have, the less pressure. Now, while we're talking about pressure, these are the ones you need to memorize. And you know, when I say you need to memorize, you really need to memorize these. Okay, you're going to need them. Just like the polyatomic ions, you needed them. So here are some. Let's see, 1, 2, 3, 4, 5. We have 6. That's it. Just 6. These are all the different units for pressure. And every single one of these is exactly the same. 1 atmosphere is the same as 760 millimeters of mercury. This is what it is at standard pressure, atmospheric pressure. It's the same as 101.3 kilopascals or 101,300 pascals. This should be a little k, big P, A. Pascal's the guy's last name. That's why it gets capitalized. Torr is also 760, and at standard pressure, it's 14.7 pounds per square inch. You might see it's PSI, especially if you choose to go into engineering. It's really more PSI. It's easier to type. It's easier to see. But LB over IN squared is also the same thing. So these are what we have at standard pressure, and we're going to use these to convert units because there's going to be times where we're using pressure and it has to be in a certain unit in order to work. So if we're looking at A, okay, I'm right here, 745 millimeters of mercury, and I want that into kPa. So I put millimeters of mercury on the bottom because that's what I have. What I want is kilopascal, so that goes on the top. There's 760 millimeters of mercury for a 101.3 kilopascal. So that's going to equal 99.3. Very significant figures. B, we have 16 and a half atmospheres We want to go from atmospheres to pounds per square inch. 1 atmosphere is 14.7. So I do 16.5 times 14.7. I get 243 pounds per square inch. Okay, so that's all we're doing. You'll notice these conversion factors right here, these values we get from what we memorized. That's why we need to memorize them. So those are all the same. The difference is we want to make sure that our units cancel, so it's on the top and the bottom are the same. And you're left with the answers they're asking for. Okay, we'll do another one. C is 11.3 pounds per square inch. So we do PSI on the bottom and KPA on the top. So it's 14.7 is our pounds per square inch number. 101.3 is our KPA number. Multiply across the top, divide by the bottom, I get 77.9 KPA. And our last one, why don't you pause it and try it on your own, and I'll put the answer up. You should get 0.9941, 4 significant figures. The reason it's 4 because this has 4 digits, so your answer has to have 4 digits. Okay, whatever they start you with, that's how much you should have. A barometer is an instrument used to measure pressure. So when they say the barometer's dropping, the barometer's rising, they're talking about the pressure in the air. Normal sea level atmospheric pressure, it should be 1 atmosphere, 76 millimeters of mercury. But you know how low pressure systems come in, high pressure systems come in. We use a barometer to see how that's fluctuating, to see if we're going to have good weather or bad weather. Now temperature in Kelvin, we've done this before. Kelvin is Celsius plus 273. So negative 16 plus 273 equals 257. 212 Kelvin, we want Celsius, I'm going to take 212 minus 273. We get negative 61. Over the other side, we have 8.7. 8.7 plus 273, sorry. And you're going to get 281.7. Remember, when we're adding and subtracting significant figures, we go to as many decimal places. So this has a 10th place, so this needs a 10th place. 0 degrees Kelvin is 273 Kelvin. Now you're going to see this a lot, STP. That means standard temperature and pressure. And it's a pressure and temperature that scientists has agreed upon to be like the overall, the standard. So for pressure, it's any of the ones you memorize. So 1 atmosphere, 760 millimeters of mercury, etc. Okay, the ones in the box right above. For temperature, it's 273 Kelvin. Okay, so you really have to know that one number, 273. So when it says STP, that's what they're talking about, standard temperature and pressure. We're going to get into 3 laws in this lecture. The first one is Dalton's law of partial pressure. And Dalton said that the sum of the partial pressures is going to equal total pressure. So if you add them all up, you get a total pressure. Kind of makes sense. So his equation is your P total equals your first pressure plus your second pressure plus your third pressure, etc., etc., etc. However many pressures you have, you add them up, you get your total. There's no visual for this, sorry. Visual's coming on the next one. So whatever pressures you have, if you add them, you get your total pressure. I'm going to look at example B first. We have what's the atmospheric pressure, so they want total. That's what that means. If the partial pressures are 604.5, 162.8, and 0.5. You take 604.5. Make sure they're all in the same units, otherwise you can't add them. 162.8. This should be a millimeter, sorry. And 0.5. We add them all up, we get 767.8 millimeters of mercury. Okay, so it's what Dalton says, you add up all the partial pressures and you get the total. Now if we look at A, it's a little bit different. They give me the total. They want to know what 33% of that is, because a person's using an oxygen mask and they're breathing air at 33% oxygen. What is the pressure of oxygen if the total is 101, is 110 kPa? So this is a regular percent problem from when you were younger. So they're basically saying, what is 33% of 110 kPa? We're going to take 110 times 33 over 100 to get out of its percentage. And you're going to get 36.3 kilopascals. And our final example of Dalton down here gives you a hint to use table A8 in your text. Now on tests and quizzes, I will give you all the partial pressures for water. But this table gives you the pressures of water. And at this temperature, 20 degrees Celsius, it's 17.5 torr. Okay, so oxygen gas from decomposition of potassium chlorate was collected by water displacement. The barometric pressure and the temperature during the experiment were 731. So that's your total. At 20 degrees Celsius, what's the partial pressure of the oxygen? So we have total equals the pressure of the oxygen plus the pressure of the water. Okay, so I have 731.0 torr equals pressure of the oxygen plus 17.5 torr. So the pressure of the oxygen is 713.5 torr. So this one you had to use the table in your book. Like I said, you will not obviously use a table in your book on tests and quizzes. That number will be given to you. All right, we have two more laws to do. First one is Boyle's law, and that's going to look at pressure and volume. And it says that the volume of a gas is indirectly proportional to the pressure. Okay, so here's the equation. P1 V1 equals P2 V2. So what they're saying is as you press down on this, you're applying more and more and more pressure. So your pressure's going up. And as you're squeezing it, right, this is coming down and this is staying the same. You're squeezing it down, you're going to get less volume. Now, okay, so pressure goes up, volume goes down. That's indirect. So if you start, and this is exactly the picture above is, if you start with a piston way up high like this, trying to draw semi-what's up above. Okay, you've got a piston in here, you have your gas molecules. As you apply pressure, we're going to push that top part down. It's going to make this whole part go lower, right? So you still have the same number of gas particles. Let's see, I have 1, 2, 3, 4, 5, 6, 7, 8 dots. 1, 2, 3, 4, 5, 6, 7, 8. I still have 8 dots in there, but there's a lot less volume. Okay, so the pressure is going down. So when the pressure is low, the volume is high. When the pressure is high, your volume is low. Okay, they're opposites. That's what indirectly means. So if we're looking at these, we have a volume. We have a pressure. They want to know the second volume. If we have standard pressure. Standard, remember, is the ones that you're memorizing. And in kilopascals, it's 101.3. You just want to make sure that your units on pressure match, or your units on volume. They just have to match. Doesn't matter what they are, they just have to match. So we have P1 V1 equals P2 V2, right? So we have 87.6 kPa times 242 centimeters cubed equals P2, 101.3 kPa times V2, we don't know. So V2 equals 209 centimeters cubed. Let's try one more. So we have a gas contains it with a pressure of 608 millimeters of mercury. The volume is 545 centimeters cubed. The volume of the container is increased to 1065 centimeters cubed. What's your second pressure? Okay, so for this one, it's what I do for all of them is I list the numbers I have. This will help me figure out what equation to use because we're going to have lots of them by the end of the chapter. So I have pressure and volume. And let's see, my units are the same, so that's good. My answer is going to be millimeters of mercury. 608 millimeters of mercury times 545 centimeters cubed equals P2, times 1065 centimeters cubed. So your second pressure is going to be 311 millimeters of mercury. Last law for today, or for this lecture. The volume of a gas is directly proportional to temperature. So V1, over T1 equals V2 over T2. Now visually, if you have a balloon, and usually the Mylar ones work best, it's a nice, warm, sunny day. Your balloon looks like that. Now let's say it's not a warm, sunny day. You buy it at the store, it looks like this, and then you go outside, and it kind of crinkles, and you think you lost some money. You think it's actually lost air, and you bring it back in the store to get it refilled, and you go back in the store, and it's poof, it's back the way it should. It's because as the temperature goes up, your volume is up. If the temperature goes down on a cold day, your volume is going to go down. Okay, that's what it means by directly proportional. Notice when it's direct, we divide. Okay, just a little hint there, the two D's, a little alliteration. So take a look at these. We have 20 liters, so that's a volume. We have temperature, T1 is 100 degrees Celsius. And right away we're going to change into Kelvin. We cannot use Celsius. T2 is 0 degrees Celsius. V2 is what they're looking for. So we're going to plug it into our equation. V1 over T1 equals V2 over T2. So we have 20.0 liters over 373 Kelvin. And that's going to equal V2, which we don't know, over 273 Kelvin. Now notice I listed all my variables. That way I knew exactly which equation to use. I'm not using P1 V1 because I don't have pressure. I have to use V1 and T1, which is a division. So V2 is 14.6 liters. Listing your variables is going to help you a lot as we continue on in this chapter. All right, last example. We have 1 liter at 255. So V1 equals 1.00 liters. T1 is 255 Kelvin. Already in Kelvin, which is nice. They want to know T2, but V2 is 0.45 liters. So I'm going to plug it into my equation. V1 over T1 equals V2 over T2. And I have 1.00 liters over 255 Kelvin equals 0.45 liters over T2. Your little cross multiplying, T2 is 120 Kelvin. Now, honestly, it came out as 115. But I can only have two significant figures, so I had to round it to 120 Kelvin.